Yeah, thank you everyone for joining us. So this is Wang Dazuo. I'm professor at the Architecture Engineering Department at Pennsylvania State University. Today is our great pleasure to welcome Dr. Cary Faulkner from the Pacific Northwest National Laboratory to give us a lecture using Modelica to model building VAVA systems. Dr. Faulkner received his PhD from University of Colorado Boulder. He did amazing work. So he's my PhD student. Yeah, he worked on many different systems, including the air-based system, but also the chiller plants with the water standard economizer, which leads to the publication for ASHRAE 1661 project. And he's going to present that in the ASHRAE Winter Conference in January. And after graduation, he worked at PNL and did a lot of amazing work using those Modelica models. I think today we're looking for his updates about the progress he's made. Without further ado, let's start the lecture. So the audience, if you have any question, feel free to type them in the chat window. And then we will try, if simple clarification questions, and Dr. Faulkner can answer you. Otherwise, we can reserve discussion at the end of his lecture. Okay, so Cary, the floor is yours.
Great, thank you so much for the introduction. Let's see, did it start sharing? Hold on, nope, I don't think it did. There we go. Okay, that should be good. Yeah, thanks for the introduction. As mentioned, today I'm going to be talking about modeling VAV systems using Modelica and some applications for healthy and reliable buildings. Can you see the screen okay? Does it look good?
Yeah. Yes, it's good.
Good, good. Okay. Yeah, Dr. Zuo introduced this a little bit, but just quick about my background. I received my bachelor's in mechanical engineering from Purdue University before joining the Sustainable Buildings and Societies Lab at with Professor Wang Zuo at CU Boulder, where I got my PhD and finished that a couple years ago. And I've now been a mechanical engineer in the Building Simulation and Design group at Penn for almost 3 years now. And my research interests include building system and indoor environment modeling, which I'll certainly talk about today, healthy and reliable buildings, as well as AI for advanced building controls. So the outline for today's presentation, we'll start with just the background on VAV systems and then talk about the modeling objectives for these systems, and then looking at modeling these systems using Modelica in terms of the different components within the system. And then lastly, we'll discuss some applications of these models to simulate HVAC operation for healthy, reliable, low energy use, and comfortable buildings. And then some conclusions. So let's start with what is a VAV system. Well, VAV stands for variable air volume. By this, it means that the airflow rate supplied by the HVAC system is variable, which I'll contrast to constant air volume systems. So typically the strategy is that the HVAC system can vary the airflow rate, and then perhaps the supply air temperature can be held constant from the air handling unit, and just the airflow rate can be varied to try and meet heating and cooling demands. So this contrasts with a constant air volume system where the airflow rate is held constant. It's maybe a just on-off single speed fan to supply air to the building, and then the supply air temperature might be variable to meet the heating or cooling loads. So this is kind of an example of what those airflow rates could look like, where that top plot just shows more of a constant air volume system. There might be some ramping when you turn the fan on and getting the system moving initially, but it's just going to be more of a constant flow rate. Whereas then on the bottom, you have the VAV system, which might modulate the airflow in order to meet the heating or cooling demands. So then what are the sort of trade-offs between these two different systems? Like why would you choose one over the other? Constant air volume systems might have lower initial costs. They're kind of simpler systems. They're good for, single zone systems or maybe homes um, that are, or smaller buildings with more constant ventilation loads, and you can just kind of turn them on and off to meet the loads of that building. Whereas VAVs are going to be more commonly used for larger buildings, especially larger commercial buildings. They can be more energy efficient because you have this aspect of being able to change the airflow rate and potentially avoid overcooling or overheating, as well as just maybe a better, more optimal way to provide air into the building by modulating the airflow rate. As well as you can, for multi-zone buildings, you can meet varying demands of those zones better, and perhaps have better control over individual zone temperature through that airflow modulation. So let's break it down to the different components, key components of a VAV system. First, you have the air handling unit, or the AHU. And this is going to include your fan, which for a VAV system is going to be some sort of variable frequency drive fan that is going to be able to modulate the airflow and provides that variable airflow aspect of the VAV system. Typically at the air handling unit, you're also going to have cooling and heating coils to condition the air supplied to terminal units. The air will also typically be a mix of outdoor air and recirculated air that you condition before supplying to the terminal units, which I'll talk about on the next slide. But you can see sort of downstream of the air handling unit, you supply that air and then perhaps at a variable rate, but then also you have these VAV boxes that open and close to control the airflow to individual zones and sort of condition those zones more, potentially separate from each other. Although what's happening upstream is going to be the same air. So, for example, the VAV box can open or close depending on the heating and cooling demands from, or ventilation demands from, those individual zones. So now let's talk about those VAV terminal units, also known as VAV boxes. These are a critical part of the VAV system because at each of the zones, which could either be, individual room or maybe a group of rooms, a group of office spaces, then you have these boxes that have two key aspects, I'd say. Controlling the airflow using these dampers based on, how much ventilation or heating and cooling is needed at the zones, and then reheat coils, which can enable sort of the additional temperature control. And so I'll talk about this a little bit more, but based on, there's sort of a feedback loop between what's happening at the air handling unit and these dampers, where the dampers are going to open and close, and that's going to tell the air handling unit something about how much airflow is needed for these zones. And then the dampers will typically open and close to provide cooling as well as ventilation. And then reheat can be used to sort of precisely control the heating needs at each zone, as typically, especially in large commercial buildings with core zones that don't have exterior walls, then there's always going to be some amount of cooling needed as like people and equipment generate heat, but then you can allow for reheat at those zones that maybe don't always need cooling and require heating. So now let's talk about some of the controls related to the both air handling unit and terminal units of the VAV systems. So first, that fan, it's not necessarily going to be controlled to meet a constant airflow set point, of course, because it's going to be variable, but it's going to be controlled to meet a constant pressure set point, which is going to be different. And in particular, the static pressure reading of the sort of air handling unit control is going to be based on how open or closed those dampers are. As the dampers open more, the static pressure will drop as there's less resistance to push the air through the system, which can tell that, as the static pressure drops, and the fan needs to work harder to meet that pressure set point and thus provide more air, which is sort of what the zones are telling you when those dampers are open, that they need more air. where uh, conversely, as the dampers close because the zones don't need as much air, then that's going to increase the pressure set point, and then the fan can kind of slow down to maintain that constant pressure set point. So really that pressure is a key part of the fan control and how that airflow is modulated based on the downstream needs of the zones and with those damper physics. Um, Whereas then at the central air handling unit, the supply temperature might be a constant set point like 55 Fahrenheit or 12 degrees Celsius, which is going to ensure that you're going to have enough cooling. That's going to be, cooler air that's going to ensure that the zones that need cooling will be able to be sufficiently cooled. And then you have the reheat downstream to um, provide heating to zones as needed. And then, as well as I mentioned, yeah, then you have the dampers downstream are controlled to either supply minimum ventilation needs or meet the cooling demand when cooling is needed. And then the reheat coils are controlled to meet the heating needs of those zones. So these are sort of the typical controls that maybe include like a constant pressure set point, constant supply temperature, and then those local controls for the terminal units. But maybe we can think about how these controls can be improved, which is going to inform some modeling research later on, I'd say. So there are more advanced VAV controls, generally separated into a few different categories. The first one being rule-based controls. And these rule-based controls can reset set points like static pressure or supply air temperature based on measurements taken from the building system. One example of this is guideline 36, which is going to measure things like the damper and valve positions or temperatures for the zone, air handling system, and outdoor air temperatures, and use that to reset those set points strategically, but in some rule-based manner that's going to be maybe more intuitive and interpretable, but requires implementing some sort of logic to do the control reset based on these measurements. Another category of more advanced controls that are being explored for VAV systems are model predictive controls. In this way, you can modulate the set points by essentially solving a optimization problem using some sort of model over a fixed horizon. And this is, potentially useful because you can leverage models to be able to predict what's going to happen in the near future and then use that to determine what's the optimal set points. But I'll talk about some of the downsides of that as well. And then another popular area right now are data-driven controls, perhaps using AI algorithms to learn to control these set points to maybe near optimal like system operation using measured data. And of course, with modern AI, this is definitely a hot topic. Reinforcement learning is one example of this that sort of trains an agent to perform the optimal actions based on either rewarding or punishing it based on the outcomes of those control actions. But advanced controls, while I think interesting and showing great potential, they certainly have challenges. In general, they can be difficult to implement, or certainly at least more difficult to implement than just constant set point controls. They might require significant knowledge to either model the system or significant data requirements to train these AI algorithms to learn how the system is operating. As well as then the data-driven methods, even maybe some of the model-based methods can sort of lack interpretability as it's unclear what exactly the control actions that are taken or why they are taking these control actions if it's sort of in some sort of a black box environment. So that's the background on these VAV systems. And now I'm going to use that to kind of motivate how we can model these systems. And in particular, first, what are the modeling objectives for modeling VAV systems? So first, what do we need to model to faithfully represent a VAV system? And it's going to depend on the applications. But let's say for building energy and control studies, which is going to be a common application, broad application of VAV systems. I think, probably the most important thing is going to be the airflow physics, right? That's the key part of these airside VAV systems. And one aspect of this I mentioned is the coupled pressure flow relationship. As I mentioned with the fan control and the dampers, there's this pressure aspect that's going to control the fan and inform what's happening at the zones, and that's going to be tightly coupled with the airflow. And so being able to model that relationship is perhaps critical. Then obviously we need the sort of thermal and energy dynamics. This includes like the heat transfer from the coils or from the zones, and then coming back to the air handling unit from the return ducts, and then the energy consumption to model the energy usage of the coils or the fan, things like that. And then the last, I think, key aspect that those are kind of more the fundamental physics of VAV systems, and then there's the control aspect, which obviously connects to the physics, but it's going to be how these systems are controlled. And this includes the supervisory controls, which is more of like what's happening at the set point level at the air handling unit, for example, or at the zone set points. So for example, the static pressure set point of the air handling unit or the supply air temperature of the air handling unit. But then you also have local controls, which is more of like what's going on in terms of how are these components like dampers or coil valves are being actuated to meet the desired set points or whatnot. And then connected with that is the actuation, how we can model the movement of valves and dampers and things like that, which sort of connects the controls back to these physics. So now I'm going to talk about how we model these aspects in Modelica with an example for a VAV system for a medium office building. So starting from the top level, this is what this system model looks like. It's in the Modelica Buildings library. It's a single floor which includes 5 zones of an office building served by a VAV system. It has a chilled water cooling source and a hot water heating source. And this is maybe sort of a prototypical configuration of a VAV system for an office building. And it includes different aspects beyond the VAV system in this model, but I will kind of focus more on the VAV part. So let's start with the VAV system model. This is, if you're familiar with Modelica, then it's hierarchical, and that first slide, or the slide I just showed, is more of the top level of the model, and this is now exploring the VAV system model within that. So let's start by breaking this down because these Modelica models could be a little messy, but the first key aspect is the airflow path. I mentioned that in the modeling objectives is modeling the airflow physics. And so this is going to include sort of a path between the outdoor recirculated air, then being supplied to the zones, and then returning back through the air handling system. So sort of in the bottom left corner of that airflow path is going to have your outdoor air source to draw in outdoor air and your mixing box to mix the recirculated air. And then it's going to pass through these coils and have the fan, draw and move that air through the supply duct and then connect to the zones on the right hand section of that figure. And then there's also the connection to the zones to have the air return from the VAV or from the zones back into the air handling system through the return ducts, where it's either exhausted to the ambient or recirculated back through the air handling unit. And then there's also this section here, which describes some of the controls and includes the logic needed there to control things like the fan and the coil valves, which I'll talk a little bit more about later. And then there's the connection to the water sources as well to provide the heating and cooling. And now let's talk about some of those controls at the top level of the VAV system model. So first is the supply air temperature control from the air handling unit. If we open up that block, this is what it looks like, but I'll try and break it down a little bit more. So the first aspect of the supply air temperature control is controlling the heating coil valve at the air handling unit to meet the SAT set point. I mentioned the central air handling unit has both a heating coil and a cooling coil, which have water sources and valves to control the water flow through those coils. So that first aspect is going to take information from this PI block based on the measured and supplied temperature set point. Or the set point for the supply temperature and the measurement for the supply temperature, and it's going to be fed up into this block here and determine based on those measurements, and some mapping, how much heating is needed at the central air handling unit to meet the set point. Now, typically, I mentioned, these VAV systems, they have reheat downstream, and the uh, supplier temperature might be something just constant like 55 Fahrenheit. And so because of that, you're typically only going to need heating at the air handling unit during the coldest times, because the reheat can cover the rest of the load. So it's really when you're bringing in enough cold outdoor air that when it mixes with the return air, that it's going to drop the temperature low enough that you might need a little bit of heating to just um, to meet that supply air temperature set point. And then the next aspect of this control is going to be the outdoor air economizer cooling. So I should mention that this system includes an economizer for outdoor air, which allows the potential of free cooling when conditions are favorable, particularly when it's cool outside, but you still need cooling in the building, especially with people and equipment generating heat. So that's going to prioritize cooling the zones using outdoor air. And there's going to be a sort of a similar signal from that based on the supply measurements, supply temperature measurement and set point, and then the outdoor air temperature. And then the last aspect is then going to be controlling the cooling coil valve to then meet the supplier temperature set point when cooling is needed, as well as when the economizer is either disabled because it's too hot or humid out, or it just can't meet the set point alone. So that's going to be that last block there. And now let's talk a little bit about the outdoor air economizer control for these systems. So this is going to connect with how much outdoor airflow is going to be brought into these VAV systems, and it's applied to the zones downstream. There's sort of three priorities for the outdoor air economizer. The first priority is to prevent freezing of the coils, because if the coils freeze due to bringing in too much cold outdoor air, then you're going to have major problems for your HVAC system and your building as a whole. So the first is just including this PI block to ensure that you're not bringing in enough outdoor air to freeze the coils. I should mention, a common theme in these controls within Modelica is having these PI blocks, which are connected to the measured, some sort of sensor measurement, and then the desired set point, and then it's going to feed that PI signal downstream to some sort of actuation. And so that's what a lot of things you'll see here is these PI blocks connected to inputs or measured inputs or set points. So then the second priority is to provide the minimum outdoor airflow for sufficient ventilation, for example, defined by standard 62.1. For commercial buildings, need to be able to provide that sufficient ventilation to make sure people aren't having discomfort or being able to breathe fresh air. So that's the second priority, is just ensuring that you're bringing enough outdoor airflow to meet that set point. And so similarly, there's going to be a PI block associated with that. And then the third priority is then, increasing the outdoor airflow to target for how much is desired from economizing. And so that connects to that other block that we had on the last slide. And so if, there is some signal for bringing in more outdoor airflow and you can meet those first two requirements, then you can increase the outdoor airflow to be an energy efficient way to provide cooling to the building. So that was talking about the air handling unit portion of the VAV system, and how that's modeled in terms of the airflow physics and the controls. So now I'm going to shift towards talking about the VAV terminal unit or boxes and how those are modeled. Let's start here. I think the first aspect I want to mention is, the VAV systems are often used for an air handling unit that's serving multiple zones, and thus they might have multiple VAV boxes or terminal units for one air handling unit. And this model on the right here that I've opened up from the VAV system model here, this shows one VAV terminal unit model, but it can be easily vectorized and then connected to the air handling unit model to show, multiple similar VAV terminal units for one air handling unit, which is a convenient way to model these components in Modelica. So then the first key aspect of this model is the dampers, which is highlighted in the center there. And that's going to connect with the airflow path from the VAV system, as you can see through that blue line. And that's going to include some sort of control to open and close the damper and then model the airflow physics and the sort of pressure flow relationship to determine how much flow is provided to the zones downstream and connect back to the pressure flow physics at the air handling unit. And then we have the heating, the reheat coil valve. Um, a lot of times VAV systems might have electric reheat coils, but in this model, it's a hot water heating coil, which includes a valve to modulate the airflow, modulate the water flow through the reheat coils to meet the reheat demand. So you can see a different blue loop there representing the hot water loop and connecting to the hot water sources to model that flow of water through that. And then you have the bidirectional flow of water through the heating coil within the terminal unit itself. So now let's talk a little bit about the terminal unit controls. We'll open up with this model block first, which shows the inputs being the room temperature set points for heating and cooling, as well as the measured room temperature. And then these are going to inform what needs to be done for the damper actuation and the reheat coil valve actuation. So let's start with the reheat coil valve. That's going to be controlled to meet the room heating set point when it's determined that heating is needed. You'll see the PI block there, which takes the room temperature, measured room temperature and heating set point as signals for the PI block. And then, it depends on the specified control of these systems, but oftentimes the airflow from the system, from the VAV terminal unit to the zone is constant during heating, and then you just modulate the discharge air temperature using the reheat coil to meet the heating demand at the zones. But there's also other controls that might modulate both the airflow and the discharge air temperature for heating to meet the zones. I think in this case, it uses a constant airflow set point during heating. And then the damper is then controlled, one, to provide the minimum airflow, so either like a constant heating set point or a constant airflow set point during heating, or just provide minimum airflow for sufficient ventilation to the zones. And then, of course, it might increase beyond those minimum set points to meet the cooling set point. So that's why it's important that, the supplier temperature upstream from the air handling unit is cool enough in order to be able to, there's no recool coils in these systems typically. So it's just you modulate the airflow using the damper to provide enough airflow to meet the cooling set point. So now we've covered these different aspects of the VAV systems, including the air handling unit, the terminal units, and the controls. But I want to highlight a few key challenges before talking about some of the research applications of these systems. So one, maybe you can tell these are complex multi-physics systems. They involve, you know, airflow dynamics, heat transfer, water flow dynamics, controls. And so there's certain just complexities in just creating and modeling these systems. There's also these different aspects of, faster dynamics, for example, the controls and the actuations of those controls with slow dynamics, like for the building thermal dynamics, which are going to tend to be inherently slow, especially for high thermal mass buildings. And this can create some numerical challenges as you want to be able to capture some of those fast dynamics to faithfully model the actuation of the VAV system, but you also have these very slow dynamics going on as well. There's also the pressure flow coupling, which I highlighted as important to model for these systems to be able to, really capture that relationship between the dampers and the fan in a sense, how that informs what the fan is doing to provide enough airflow to meet the demands of the zones. And while that's important to model, it introduces some more complexity as there's some numerical challenges to sort of couple the pressure and flow, and it requires additional equations to describe what's happening between pressure and flow, and can certainly add some more numerical challenges to these simulations. And this is why sometimes other models sort of simplify this and decouple pressure and flow just to make it less numerically challenging, but you might lose some important information when doing that. And then one more key aspect is um, there might be challenges integrating these types of VAV system models with more detailed room thermal models. For example, coupling with like a computational fluid dynamics model to model the uh, non-uniform thermal distribution of a zone, because this sort of comes back to how these VAV system models already have, some amount of numerics that they're dealing with and are trying to capture some of these fast dynamics of the control system, but then adding, something like a CFD model on top of that is very computationally demanding as well. And so that's makes it tricky to couple. And oftentimes these models might be more isolated. So those are some of the challenges. And now I'll go into some applications of these Modelica VAV system models for various research applications. All of them will use sort of the same base 5-zone medium office VAV system model that I introduced previously, but just for various applications. So this first one is um, looking at the HVAC operation for mitigating indoor virus transmission. Particularly, this was a hot topic during the pandemic and remains an important topic now. So the research question that we aim to answer here was looking at how different levels of HVAC filtration compare against 100% outdoor air ventilation for mitigating indoor virus transmission. And we applied the Modelica-based office model I mentioned for the VAV system for an office building, but we created some new models in order to support this analysis, specifically for HVAC filters within the VAV system and virus transport for how that moves from the zones and recirculates back through the HVAC system. And doing so, after completing the modeling, we ran simulations for different levels of MERV HVAC filtration, looking at MERV 10, MERV 13, and HEPA, the most sort of efficient HVAC filtration, and compared that against 100% outdoor air for an office building in Denver. And then we compared the results in terms of infection risk and energy use among those different strategies. And I'll talk a little bit more about the modeling and the results here, but this is all published in this paper in Building an Environment. So first, we wanted to model the HVAC filters, of course, in Modelica and incorporate them into our Modelica-based VAV system model. So this is the little icon for what the HVAC filter looks like. It has those flow port connections and is implemented within the air handling unit airflow path between the or alongside the coils and the fans in the air handling unit model. So you have your flow in through the filter and your flow out. And the key aspect of this filter, there's two key aspects I'll talk about. First is then it's going to remove virus or some sort of contaminant concentration based on a assumed constant filtration efficiency. So that equation there shows that the removal is based on the concentration and the filter efficiency. And really, I should include if it's the rate of removal that will be dependent on the airflow rate, but that that efficiency value is just assumed to be constant and independent of the airflow rate. And then the second key aspect is the pressure drop that the filter can impose on the HVAC system. This is really important for a couple of reasons. When I talked about that pressure airflow relationship being a key part of these air handling systems, as well as, moderate HVAC filters might have a smaller pressure drop or resistance that is imposed on the airflow of the HVAC system. But as you get to these more efficient HVAC filters, it can become quite difficult to require significant power to push the airflow through these finer filters. And it can actually have a more significant effect on the HVAC operation, either just causing the fan to need to work really hard to push enough air through the system, or even resulting in reduced airflow rates. And so we want to be able to capture this pressure drop that is imposed on the HVAC system from the HVAC filter. And we describe this using a assumed quadratic relationship between the mass airflow rate and pressure. And then we define some nominal settings to sort of create a pressure drop curve, define the pressure drop curve as a function of mass airflow rate. And those nominal settings are going to be different for different filters and sort of define the differences in the pressure drop curves for different filters. We also add some indoor virus transport modeling. So this is going to include, or we're going to start from the mass balance for the virus concentration within the zones. And this describes the rate of change of virus concentration or some sort of biological pathogen concentration within the zone. You have, in this case, the virus can enter and exit the zones through the HVAC system, where it might be exhausted to the ambient environment or recirculated, but filtered and returned to the zones. There's also going to be some airflow modeled between the neighboring zones and exfiltration to the ambient. And then there's also the generation term and the decay term. So the generation term, I'll talk about in a second, but that's going to come from the sick people. And then the decay is sort of just the natural death of the viruses in the air. And this is modeled using a first order constant based on a constant value and the concentration within the zone. And then the generation term, we model assuming a constant generation rate from sick people when they are present in the zones. So if you're familiar with Modelica, then you can define these tables, which can introduce like a schedule to the model. In this case, I showed an example of just a typical worker working 9 a.m. to 5 p.m. in this office building Monday through Friday. And then that can be multiplied by some sort of constant to describe the generation rate, or it could be connected to something else which describes a more variable rate, but this is how we did it, and that 5 divided by 3600 being 5 quanta per hour in this case for our simulations. So quickly, some results and conclusions from this. As I mentioned before, we compared 100% outdoor air usage against MERV 10, MERV 13, and HEPA filters. This plot on the top right shows the probabilistic infection risk that we calculated for one of the sets of scenarios from the study, where on the y-axis it shows sort of like the probabilistic predicted number of infections, where that 1.0 is predicting about one infection to occur that day. And the results showed that 100% outdoor air led to the least infection risk compared to the other methods, but had a significant energy penalty, especially during the cold winters of Denver in this study. I'll talk more about that in a second. And then the HEPA filtration, while these HEPA filters are the most efficient in terms of capturing small particles, they can impose a significant pressure drop on the system. And for our simulation setup, we did find that the significant pressure drop from the HEPA filter had a negative impact on the HVAC system operation, in particular, large increases in fan power and reduced airflow rates, which led to limited infection risk reduction because of those reduced airflow rates. Even though it was doing a good job capturing the particles, it just wasn't pushing enough air through to the zones. And then we found that MERV 13 offered a good balance between infection risk reduction, as maybe not as low as infection risk compared to 100% outdoor air, but just above that, with a pretty small impact on energy use, as these filters impose some pressure drop on the system, but not nearly as significant as the HEPA filters. And in particular, that energy use on the right there highlights the monthly energy use, and there's a lot going on, but the key takeaways is that the HEPA filters sort of have high fan energy. Like you can see some of these bars here, especially during the summer when you need to push a lot of airflow to the zones. And then the 100% outdoor air has significant heating penalties in the cold winters of Denver in sort of November through February. So I'll talk about the next application. This is some of my research I've done at PNNL, but is closely related and extends some of the previous work that I just talked about. And this is comparing the effectiveness and energy use to meet infectious aerosol control targets through different airborne pathogen mitigation measures. So the research question we aim to answer here is, how do the effectiveness and energy use of these pathogen measures compare to meet infectious aerosol control targets defined by standard 241 from ASHRAE and CDC? And included in these, we apply the Modelica-based VAV system model once again, but we create some new models to be able to analyze these various airborne pathogen mitigation measures. And that includes some of the strategies I mentioned before, like outdoor air ventilation and HVAC filtration, but we also create new models for portable air cleaners to be placed in rooms and filter pathogens, as well as germicidal ultraviolet systems, both in the duct and in rooms, which irradiate in the duct or zones and inactivate the pathogens through that irradiation. And then we simulate those various measures to meet infectious aerosol control targets defined by CDC and standard 241. And similarly, I'll cover some of the models development from this work and results, but there's more to be read about this in this paper in Building an Environment. So kind of a similar format as the last one. I'm going to talk about some of the new models that we created in Modelica to support this analysis. First is going to be the in-room GUV, the germicidal ultraviolet models. This is going to describe the rate of inactivation of pathogens based on several key model parameters that sort of describe the irradiation from these systems, as well as the susceptibility of the pathogens to that irradiation. So the key inputs to this model is the zone concentration, as that's going to determine, how much pathogens are inactivated, as well as we include this signal to turn these systems on or off. And then the key outputs are going to be just the rate of removal of the pathogens from these systems, as well as some energy outputs that can be useful for just tracking energy, and then heat dissipation, because these systems consume electricity, which is then ultimately dissipated as heat to the zones. And then we have these portable air cleaner models as well that we created. These they're similar in a sense in terms of the inputs and outputs compared to the GUV model and how they're used within the Modelica system model. Um, but the, I guess, underlying described physics in the middle is going to be a little different. Where in this case, the rate of removal of pathogens by the PAC is described based on a concentration, or sorry, well, the concentration as well as the filter efficiency, and then the uh, airflow rate of the PAC. This sort of the combination of those two terms is often known as the clean air delivery rate of a portable air cleaner. So it describes how efficient it is at removing the particles and then also how much just clean air is being delivered from these systems. But similarly, it takes the zone concentration as an input and some signal to turn these systems on or off, and then outputs the same rate of removal, energy outputs, and heat dissipation. And then the last model I want to mention, this is a induct GUV. So it is similar to the in-room GUV, but the in-room GUV and the PAC, those would be incorporated into the models within the zonal models, whereas the HVAC filter and then the induct GUV are incorporated into the air handling unit model within the VAV system. And this is going to model the flow past the system and use that to sort of similar to the filter, calculate uh, the rate of inactivation and then the outflow concentration of pathogens based on a inactivation efficiency. And in this case, these the inactivation efficiency is closely related to the airflow rate because, for example, these induct UV systems are going to irradiate some sort of space within the duct, and the pathogens will be inactivated based on how much time is spent in that irradiated space. So if the airflow rates are really high, the airflow is moving past it very quickly, it's the uh, less time will be spent in that irradiated space compared to if the airflow is moving more slowly. So we model this phenomenon based on sort of using a dose relationship between the um, that describes the amount of time that the pathogens spent in that irradiated space and how much dose they receive from the system, and connected with the airflow rate, which then describes, um, you know, connects with the amount of time that the air is spending in that space. So this plot on the right shows in black just a how if you linearly increased the airflow rate from, you'll see on the right y-axis, 25% of the nominal flow rate up to 100% of the nominal flow rate, then how the estimated inactivation efficiency decreases from, close to 100% to closer to 65%. And this is described by an exponential relationship. And then we, of course, have our flow in and flow out energy outputs and the on-off signal for these devices. I'll talk about some of the sample results from this. So this one, it focused more on the energy aspect as well as calculating these equivalent clean air targets compared to infection risk modeling. And so in particular, around the time of the pandemic, the CDC defined an equivalent clean air target of 5 equivalent clean air changes per hour. So a lot of times we think of air changes per hour from ventilation from the HVAC system, but the equivalent allows to count air changes per hour from filtered air, outdoor air, as well as air that's been inactivated or with pathogens that have been inactivated by the GUV systems. And so we compared these different measures, including whole room GUV, which irradiates the whole room, upper room GUV, which just irradiates the upper portion of the room, and then portable air cleaners, filtration, outdoor air ventilation, induct GUV, and then at baseline in terms of their ability to meet that target and in an energy efficient manner. And our key takeaway here was the HVAC system measures, which include maximum outdoor air ventilation, MERV 13 filtration, and induct GUV, were unable to meet the target for this office building, the CDC target here, not because they're not an effective way to clean air, but just because of the system limitations on the HVAC system. So even if they're able to provide clean air, not enough airflow was able to be pushed through the HVAC system to the zones to meet that high 5 EACH target. Whereas on the other hand, the in-room measures were able to sort of complement the baseline ventilation from the HVAC system to then meet the CDC target by inactivating or filtering particles directly in the zone themselves. And those in-room measures of whole room or uproom GUV, as well as portable air cleaners, were able to meet the CDC target of 5 EACH for offices with a low energy use per EACH as well. I'm going to go to the final application now. So the first two applications pretty heavy on the indoor air quality side and how the VAV systems can be operated to mitigate pathogens in an energy efficient manner. This side is going to go a little bit more into the advanced controls, which I touched on a little bit earlier in the presentation. And so this is a simulation-based assessment of Guideline 36, which is a guideline from ASHRAE that describes control sequences for HVAC systems, including VAV systems, to sort of improve upon those constant set points to try and improve the energy use and operation of these systems. So the research question we have here is, how do the advanced controls from Guideline 36 impact energy use? And we also did look at indoor air quality for this prototypical VAV office building system. And to do this, we implemented and verified G36 controls for various control set points within the system, including supply air temperature, duct static pressure. I mentioned those key aspects of the VAV air handling system, as well as demand controlled ventilation, which I'll talk about more, but controls the ventilation to the zones based on CO2 measurements, as well as controls for the hot and chilled water plants. So the schematic on the right, we still take that base Modelica office building system model, but we use the BOP test environment to perform a co-simulation between Python and Modelica, where these controls are implemented in Python, and then there's some co-simulation aspect there that I'll talk about a little bit more. And then also in particular for this one, there's the chilled water and hot water plant are modeled in a little more detail to look at those controls there. And we also modeled the CO2 within the zones based on human emission to inform the demand controlled ventilation. And we assess the results in terms of energy use, thermal discomfort, and we do look at infection risk as well. And you can read more about this in this paper published also in Building and Environment. So first, let's talk about the Guideline 36 control implementation. The key aspect of these controls are they reset the set points using system measurements from the building, and they reset them using trim and respond logic. So the idea here is you want to trim the set point in a way that's going to gradually save energy. You're not going to aggressively change the set point, but sort of maybe slowly trim it, and then check on measurements to make sure that you can continue to trim and in order to attempt to save energy. And then you might respond by increasing or decreasing your set point, depending on what the set point is, based on requests, these measurements from the zones. So this plot on the right just shows sort of a verification of our implementation of Guideline 36 using our models for the duct static pressure set point. I talked about how that's a key aspect of these VAV systems. So the top plot just shows the number of requests that we just manually fed to the controller. But I'll talk about what those requests might mean. And then the bottom shows how the set point trims or responds based on those requests. So when there's 0 requests, then the set point gradually trims from a very high static pressure set point to a lower one. And there's some upper and lower bounds defined there just so you don't get crazy values. And then when we have requests occur, in particular, the more requests that you have, then the set point is going to respond more dramatically. You'll see with 3 requests compared to 2 requests that increase in the set point is going to be a little bit more more requests. There's also just some amount of ignored requests where at one ignored request or at one request, then that request is ignored and you continue to trim the set point, but that's sort of a tunable parameter perhaps. But example of what might generate these requests for a VAV system are the damper position measurements. So for example, you might trim your static pressure set point, which can potentially lead to less airflow. But then if you have significantly opened dampers, that means the zones are starved for air. And that's going to generate a request that's going to be fed to this controller and say, okay, there's 2 zones that are requesting more air, and then the controller will respond accordingly and increase the set point. And then this whole process is enabled through a co-simulation platform between Python and then the Modelica models in the BOP test environment, where the measurements from the Modelica model are then sent to the controller in Python, and then the Python controller, receives those measurements, it processes it, and then sends a signal to update the set points back to the model, and then those set points get updated in the model in that co-simulation. And this all happens at some sort of synchronization interval. So there's sort of, the model simulates, and then at the synchronization interval, you have this exchange of data, and then it continues until the simulation ends. And then just quickly talk about some of the results from this. We found that the guideline 36 controls can save energy compared to the baseline control, which just used constant set points for this VAV system and hot water and chilled water plants. Should almost go back here. In particular, is able to save a good amount of heating energy by, I think, avoiding reheat, particularly by resetting the supply air temperature set point, and also maybe able to save a little bit of cooling energy. We did see an increase in fan energy, and this is related to the demand controlled ventilation, or DCV, which was a part of the controls, which increase ventilation based on the CO2 measurements in the zones. And in particular, we saw that this would happen quite often, kind of towards the end of the day. You see in the bottom plots there. That bottom plot shows, the sort of set point, or the band in which the demand control ventilation might increase based on the CO2 measurements. So as the CO2 would increase within the zones, maybe around 3 p.m. after people had been in the office for a good portion of the day, then the demand control ventilation control would respond and increase the ventilation to the zones, which would improve the indoor air quality, both in terms of the CO2 levels and the simulated virus concentration levels, as it's going to able to push more air through there, but would lead to more fan energy usage. So now I've gone through all of my presentation and just want to talk about some of the overall conclusions. So as introduced, these VAV systems are pretty commonly used for larger commercial buildings with multiple zones. They can be more energy efficient and control, varying temperatures among zones better. And then in order to model the VAV system, then there's several key aspects that we want to capture, including the airflow physics, heat transfer, and controls. And being able to model these systems using Modelica enables these analyses of building energy usage, indoor air quality, comfort, and advanced controls through several key aspects, but including capturing the coupled pressure flow relationship, as well as the control and actuation dynamics. There are still some challenges related to modeling these systems. As I mentioned, some numerical challenges, handling these fast and slow systems, and coupling with other thermal airflow models. But with that, I'd like to thank everyone for listening and open up the floor for questions.
Thank you, Cary. This is really wonderful. Okay, so we have any question from on-site people or online? Okay, maybe I can start. So that's a common question I often receive for, a typical non-expert user. So, you have done amazing work. So how can they, right, using the work you did for their, practice?
Yeah, good question. So I think, the good news is a lot of these Modelica models are open source and pretty well documented. So, the office system model that I talked about today is publicly released in the building's library. And then, some of the work that I did, not all those models are individual component models are publicly released, but they're documented in those publications as well as they are sort of built on top of existing component models within the Modelica buildings library. And so I think that's there's maybe a learning curve to learning Modelica, but once you understand it, then it's I think quite powerful for these types of modeling applications, especially those related to control and airflow. So I guess that's what I would say. There's a lot of documentation out there, hopefully to help users with this.
Excellent.
Mhm.
Okay, anyone, you guys? Yeah, go ahead.
Um, I don't know if you can hear me or not, but I was just curious because like,
You can come closer.
okay,
Say hello to him.
oh, hi.
Hey,
Great presentation. This is more general, not maybe so much related to like Modelica itself, but just like the concept.
uh-huh.
So for like we're referencing commercial buildings, VAV systems, in regard to like using advanced controls, which you had kind of talked about more in the beginning of the presentation. I assume it's not used very frequently for commercial applications, just because of how much data that you need to just have it run properly. It's very specific to your building. Um, is this something that like the industry is trying to push for? Like, I imagine you would need at least a year's worth of like zone data to kind of be able to model your VAV system properly with Modelica. So how is the industry trying to implement these sort of specific controls in just typical commercial buildings?
Yeah, thanks. This is a really great question, actually. So I would say in academia, people are very excited about the potential of these new advanced control methods, but the adoption in industry is much slower than that. For some of the reasons I mentioned, just in terms of uh, like the sort of knowledge and data requirements, as you mentioned, and I think also just there's sort of a maybe conservative aspect, like you don't want to um, mess up your like a if it ain't broke, don't fix it type of thing. But there are certainly, I think, a lot of despite that slow adoption, a lot of industry is recognizing the potential of these and are starting to maybe explore it a little more. Um, and I think one key benefit or you know good news is that a lot of these commercial buildings, especially maybe the newer ones, have a lot are collecting a lot of data because either just to help with the inform the operation of these systems, let the building operators know, what's working, what's not working. They're collecting a lot of data that can be used for modeling or data-driven purposes. So I think that's kind of the good thing there. But to create a physics-based model, especially in something like Modelica, that requires a good amount of knowledge. And then, even if you have all this data to create a data-driven model, then there's some of the downsides there I talked about, like the lack of interpretability or maybe extrapolating to new scenarios. So I think maybe to try and answer your question, the industry I think is maybe slowly moving more towards these more advanced methods, but there are still concerns and just like more things that need to be proven for it to be more widely adopted.
Yeah,
Yeah.
thank you.
Mhm.
Yeah, so great. Yeah, I also want to add something. Like, so first I would say to adopt advanced control like guideline 36, you don't need Modelica, right? So the idea that we sequence described that you can just deploy it on site. So when you need advanced modeling, like for example, if you're going to design a new system, right, a new building with advanced control, that maybe out of the box or something more creative. Then you want to evaluate if this control is going to work or if this design is going to work. Then that's the opportunity to use Modelica. So in that case, you actually don't need the historic data because it's designed, right? And
Yeah.
so most Modelica model has, the models released in the buildings library already calibrated against, the manufactured performance curve. So basically, you can trust them for design purposes.
Okay.
Right. So I feel that part you don't need it. Then if, let's say, you have an existing building, you want to use the model to help you to identify the faults, or maybe you want to deploy a new control, but you want to test it before you deploy the control. Then that you can use the historical data to calibrate the Modelica model. So basically different purposes. Yeah. So then
Yeah,
you decide if you need a Modelica model or not.
Okay. Yeah, that makes
definitely
sense.
agree.
Yeah. It's good. Okay. Any other questions from?
I have a question.
Yes.
Hi, this is Julia Ho. Good to see you, Cary.
Yeah.
Yeah, I'm a PhD student in Dr. Zou's lab as well. But I had a question about the co-simulation with BOP test. I saw that
Mhm.
you were using like a specific time step,
Mhm.
and I was just wondering if that was like a designated constant time step, or if you still maintain the dynamic time step that Modelica is able to take advantage of. And if you
Yeah.
weren't able to, does that worry you in terms of capturing the control dynamics that you'd be able to get in Modelica otherwise?
Yeah, no, thanks, Julia. That's a good question. So we still use the dynamic time step from Modelica. So
Mm,
how it works is there's a co-simulation and a connection, but the more or less the Modelica model is going to simulate as like you typically would using your dynamic time step solver, but it's just going to pause at this defined synchronization interval and then exchange data with the Python controller and then sort of continue. So there's like two different, you could think of it as like two different time steps. One is just the synchronization time step, which I think in this was like 5 minutes or something, which would
mm.
be too slow to capture those dynamics. But then within that 5 minute uh, interval, then the Modelica simulation is running with a dynamic time step solver that's going to be much shorter than that. So hopefully that answers your question.
Yeah, so like how is the Modelica model being controlled when it's not receiving the control sequence information from Python?
Okay, sorry. So it's at like you have some initialization and then it's going to run for the first set and then it'll exchange information with the Python module. It'll send the measurements from the simulation model to the Python module. And then the Python module will output the new set points and overwrite the set points in the Modelica model at that synchronization time. And so now the Modelica model has new set points, and then it continues with the simulation for the next, 5 minutes in this case. And then the same thing happens again. So the set points are being overwritten every 5 minutes and held constant at that set point during that interval. Um, does that make sense?
Yeah. Maybe I'll ask you a little bit more offline. I'll send you an
Sounds
email.
good. Yeah,
Okay,
so it's not
thanks.
instant, it's not like completely live and instantaneous, right? It's like, it's being updated at some synchronization, but then during the period in between, it's just held at some constant or at the value that it was last given, I guess.
Okay, gotcha.
Yep.
Thanks.
Hmm.
So Cary, maybe could you please elaborate even more about the Bob test? I think that's a really powerful tool for those interested in the control, design or evaluation.
Yeah, definitely. I think this was a very handy tool for us because the BOP test library has some pre-built Modelica models for including, this VAV Office System 1. I think there's others for maybe like a plant or like a single zone model and whatnot. But it wraps that Modelica model in an FMU, which is a functional mockup unit, but it essentially just like it's a wrapped model that allows you to easily interface in a co-simulation environment. And then it interfaces with Python, which like I personally love coding in Python, and like a lot of people are very familiar coding in Python. So then you can, co-simulate and interface with these pre-created models using Python, and then you can, essentially incorporate your controls in Python, whether it's an advanced control, that could be a data-driven controller, a model predictive controller, and then easily interact with these Modelica models. And so it's great for like control optimization, or maybe just more broadly, like evaluating new controls.
Great, thank you. Yeah, Hongjin also shared the link of the Bob test project. So if anyone interested in that, you can visit the website. It's a joint project led by Lawrence Berkeley National Lab. Okay, any other questions from on site here? And okay, I see any online questions. Okay, if not, okay, I think it's time we can close the lecture here. You can stop recording. Thank you everyone for attending the lecture.